Base drive control. Switching speed can be increased by reducing turn on and turn off. The turn on can be reduced by allowing IB peak during turn on, resulting in low forced gain, that is beta F. After turn on, beta F can be increased to sufficiently high value to maintain the transistor in saturation. Turn off can be reduced by reversing the base current IB, allowing IB peaking during the turn off. Increasing the value of reverse IB reduces the storage time. Now, apart from the fixed shape, that is IBS, the forced gain beta F may be controlled continuously to match the collector current variations. Techniques for optimizing the base drive of BJT: one is turn on control, second one turn off control, third proportional base control, fourth one anti-saturation control. Let us see one by one. This is base current peaking during the turn on circuit, and this is the input voltage. So when input voltage is turned on, the base current is limited by R1. That first initial base current IB1R is given by, that is input voltage VB, which is at the initial position, it is V1 minus the VBE divided by R1. This initial state. Final value IB1, this is our final value, is given by V1 minus VBE divided by the total resistance, that is R1 plus R2. That is equation number 2. The capacitor C1 charges up to a final value, that is Vc. The voltage across the capacitor is approximately equals to V1 R2 divided by total resistance R1 plus R2. The charging time constant of the capacitor, that is tau 1, is given by R1 R2 divided by R1 plus R2 C1. Once VB tends to 0, BE junction is reverse pass and C1 starts discharging through R2. Discharging time constant tau 2 is given by R2 C1. To allow sufficient charging and discharging times, the width of the base pulse must be T1 greater than or equals to 5 times of tau 1, and T2 must be greater than or equals to 5 tau 2. The maximum switching frequency f of s equals to 1 by t, that is 1 by t on plus t off, that equals to, substituting the time constants, that is 5 times of tau 1 plus 5 times of tau 2,
0.2 of 1 by tau 1 plus tau 2.
If the input voltage turn on position is charged to minus V2 during the turn off, the capacitor voltage Vc here is added to V2 as a reverse voltage across the thyristor. There will be base current peaking during turn off. As the capacitor C1 discharges, the reverse voltage will be reduced to steady state voltage V2. Now, if we need a different turn on turn off characteristics, then the turn on circuit, that's C2, R3, R4 and D added for the previous circuit. The diode D isolates the forward base drive circuit from the reverse base drive circuit during the turn off. This is an additional circuit required if you want to do turn on turn off process separately. Now, proportional base current drive. Now, this type of control have the advantage over the constant drive circuit. If the collector current IC changes due to change in the load demand, base drive current is changed in proportional to the collector current. When S1 is turned on, a pulse current of short duration would flow through the base of the transistor, and the transistor is turned on into saturation. Once the collector current starts to flow, a corresponding base current is induced due to the transformer action. The transistor would latch on itself and S1 can be turned off. The turns ratio is into by N1 equals to IC by IB, which equals to beta. For proper operation of the circuit, the magnetizing current must be much smaller than IC, that is collector current. Switch S1 can be implemented by a small signal transistor, and the additional circuitry is necessary to discharge the capacitance C1 and the rest of the transformer core during turn off the power transistor. Finally, anti-saturation control. This is the circuit for collector clamping. If the transistor is driven hard, the storage time, which is proportional to the base current, increases and the switching speed reduces. The storage time can be reduced by operating the transistor in soft saturation rather than hard saturation. And this can be accomplished by the clipping collector emitter voltage to a predetermined level. The collector current IC is given by VCC minus VCM divided by RC. That will be question number 1, where VCM is the clamping voltage. Clamping voltage VCM is greater than VCE saturation. Now the base current without clamping, which is adequate to drive the transistor hard, can be found that IB equals to I1, that equals to VB minus VD1 minus VBE to the RB. That this extra clipping circuit is not there. Then IB1 equals to IB, VB, VD1 and VBE. Distance is only the RB. And the corresponding collector current is given by IC equals to beta IB. 2 and 3. After the collector current rises, the transistor is turned on and the clamping takes place. If this conducts, this is the direction, VCE equals to VBE plus VD1 minus VD2. That is 40 equation. Then the load current IL equals to VCC minus VCE divided by RC. Now substitute the value of VCE. This will be VCC minus VBE minus VD1 plus VD2 divided by RC. Let this be question number 5. Collector current with the clamping, that IC equals to beta IB, that equals to beta IB equals to I1 minus I2. I1, I2 is nothing but IC minus IL, so IC plus IL. IC 1 plus beta equals to beta I1 plus IL. Then IC equals to beta by 1 plus beta I1 plus IL. Equation number 6. For clamping, VD1 must be greater than VD2, and this can be accomplished by connecting 2 or more diodes in place of D1. The load resistance RC should satisfy the condition beta IB greater than IL. Now from the equation number 5, IL we know, then this one is IL, then beta RC IB must be greater than IL is VCC VBE minus VD1 plus VD2. Equation number 7. The clamping action results in the reduction of collector current and almost eliminates the storage time. At the same time, a fast turn-on is accomplished. However, due to the increase in VCE, on-state power dissipation in the transistor increases, whereas the switching power losses is reduced.